Hey, so if you're watching this video, you're probably getting ready to study for that final exam. And that final exam covers a little bit of everything. Well, sort of. Okay, so this is going to be comprehensive, but it's not going to dive into all those, like, the minor parts of this course. You might be thinking, well, what is minor? What's major? Well, when you leave this course, I think it's really, really important. Then you have a basic understanding of a few things. One of those things is like beam reactions. Can you take this beam and solve for reactions? Right? Just a simple beam, simple supports. By simple, it doesn't mean easy. It means a pin and a roller. Okay, can you solve those reactions? Can you take something like this and solve for some truss forces? And once you start getting this force analysis, you get statics, equilibrium equations down. You learn how to balance things, and you learn a really, really fundamental and key concept that you're going to need in every additional course you take on here that builds on this. And that's just being able to solve for forces. Because you can't really design something for a force until you know what that force is. So in addition to that, one of the things that really comes up as well are shear moment diagrams. Shear moment diagrams is sort of like, they're so important. It's sort of like if you have a rope and you pull on that rope, you kind of know what the weight is and the weight rating for that rope is. Well, when you look at a beam, you have to understand how much bending moment is in that beam to see if it's rated strong enough. So all of these things kind of go together. Beam reactions, trusses, shear moment diagrams to figure out the forces. Now that it doesn't stop there, because this course kind of combines statics and strength of materials. And when we get to strengths, one of the things that we started to do was we looked at something like a stress strain or force elongation curve. And these curves are important because they help us understand the material behavior. What's happening when we start to pull on a piece of steel, right? It's going to stretch up to a certain point, and then it's going to yield, and it's going to permanently deform, and then it's going to strain hard, and then eventually it'll rupture. So these are kind of things, and with that, there's some equations like stress equals force over area. I tell my seniors all the time, I'm like, hey, you have to know this equation. And they're like, but didn't we learn that in like a 200 level course? And I'm like, yes, you did, but you forgot it. So don't forget it, because when you get to the fundamentals of engineering exam or future, even just engineering principles, so many of them rely on equations like this. And also when we start to look at things, we get strain, change in length over length. We get the modulus elasticity, which is the slope of this line here, right? These types of things can all get put together in something like axial deformation. Now, when we start looking at strength of materials, these equations become key. And I was just teaching a concrete design course, and we were talking about, how like stress, and from stress, or I'm sorry, strain, and from strain we get stress, and from stress we get force, and from force we can figure out member capacities. Now these concepts all go together because they help you to design better structures. Okay, so these equations are going to be in there, and even when we start to look at other things, we're going to start to look at something like this, where we look at combined stresses, maybe adding axial and bending moment, right, or flexural stress, right? And when we look at that, that's going to bring it. We have to understand tension and compression. And then in addition to that, we can look at easy, shapes or complex shapes that do not have common lines of symmetry, a common line of horizontal symmetry. And that's what we're going to be doing. So these are kind of some of those key concepts that I really want you to walk away from with this, with knowledge of in these courses. Now, did we talk about other things like column buckling? Absolutely. Did we talk about other things like Morse circle? And did we talk about things like the torque and twist, and those types of things? Absolutely. But these concepts, I think, are kind of really, really key. And as you go on, either in a mechanical branch or in a civil branch, you're going to start diving into some of those concepts more. Like when I teach a steel design course, we get into buckling and buckling and buckling. I mean, we do local buckling, we do lateral torsional buckling, we do global buckling. We really take a deep dive into buckling, right? But in order to do that, you kind of have to have some of these basic understanding of statics and strength of materials, concepts first. So these are kind of some of the concepts that we're going to work on. We're going to talk through, and these all show up in addition in some of these, in the formula sheet that I'll give you. So definitely, understand the formula sheet, understand where these components show up in the formula sheet, so that you can take advantage of them. Just like in the FE, you're going to have a reference handbook. Know that reference handbook, right? Know this formula sheet so that you can take full advantage of it. Okay, and then what I want to do here is well, it's just here's kind of a this if you're in my class, you'll have this packet with some practice problems. We're gonna go over these as well, and this kind of highlights some of the areas that I'm really gonna focus in on in that final exam. You will have a beam reactions problem. You will have a shear moment diagram problem. You will have combined axial and flexural stress where it puts both of those together. You have to understand tension compression. You will have a complex moment of inertia for a shape that does not have a horizontal line of symmetry, right? It'll be asymmetric. So you have to find a centroid. You have to find a moment of inertia using parallel axis theorem. Okay, you are going to have some trusses. You're going to have to find bar force and truss. You are going to have some of the one-dimensional or axial stress strain kind of modulus elasticity types of questions. So we're going to go over those types of questions here today. If you want more practice, there is a book on reserve in the library at Poly, and you can go get that book. It's taught by a colleague, or I'm sorry, it was written by a colleague, most recently updated. And those, some of those questions I'll throw out there. So if you want more practice, definitely you can pick up a copy of this book as well. Great resource and reference as well. So this is where it is, and what we're going to do is we're just going to jump in, and just like in past ones, I'd suggest you stop, you go do this practice yourself, and maybe you're here at the video because you've already done that. You got this far, by doing that. So hopefully here what you're doing is you're going to stop, try to take this practice exam, give yourself 2 hours, set it aside, get a calculator, get your formula sheet, go take it, and then see how you did, right? Then this will be that explanation of where it is. So we're just going to jump down here, and we are going to come in, and we're going to go to problem 1. This is a built-up steel member with dimensions indicated. It's subject to the load shown. Now, in the real test, right, when I give you a problem like this, I'm not going to give you a beam and a complex shape and lump it all together. I'm going to kind of split it up, right? So this will be one problem where we find centroid and moment inertia. This will be another problem where we find beam reactions in shear moment diagram, right? There will be another problem where you do where it's even split, where I give you a shear moment diagram, I give you a shape with a moment of inertia, and I say go find the stresses, right? So I'm going to break it up, but for the practice exam, I'm just going to lump it all together. Okay, so with this, to solve for reactions, we just have to jump in and do it, right? So this is one of those things where hopefully if you've been doing this enough, you kind of have gotten the hang of this, where we're going to draw this thing in, right? We're going to draw some some forces here, which are going to be by and dy. And right, so now we have this 3 kilonewtons down. We got this 40 kilonewtons to the left, and we have this nice big long uniform load here of 1.2 kilonewtons per meter, right? So this is it, right? But what I have to do here is make myself smaller, because that's really annoying because you couldn't see any of that. So here we go. So we have our free body diagram, and let's go and solve. Now, again, pause the video if you don't know how to do this. Go back and watch one of the other 60 videos here. Okay, but let's get started here, and we are just gonna jump in here, and we're to some moments about point B equal to 0. So when we do that, what do we get? Well, let's start with this. Let's start with dy times, I need a distance here. Let's look at this distance. This distance is going to be 3.5 meters. So dy times 3.5. I'm going to leave the units off here. Now this is units of meters. So just to save myself a little bit of room, you got to remember the units. Don't forget the units, but understand a moment is a force times the distance. So it's a kilonewton times a meter. Okay, then what am I going to do here? Maybe I'll do these loads here. I'll say the 1.2 kilonewtons per meter times a total of 4 meters, right? That gives me kind of this resultant, right? That's my resultant, and what I need is the distance between that resultant and point by. Well, if we know anything, if we've learned anything in this course, and hopefully you've learned a couple things, you know that this whole distance is 4 meters. This, it's going to be at half of that 4 meters. So you think 2, and 2 is not quite right, because we also have a half a meter here. So a half a meter, this is going to be 1.5 meters, and altogether it's in the middle of that load. So from point B though, this is going to be a distance of 1.5 meters. Okay, and then lastly here I'm going to subtract, oops, I made a mistake, you see it? I have to subtract this because this is negative, and then I'm going to subtract off 3 kilonewtons times 4 meters. Okay, so times 4. And let me just move all of this over just a hair because it's running off the page here. Okay, I'm going to say that's equal to 0. And this is our moment equation. Now, this is one of those equations that when we first started this course, this was one of those things like, what's a moment? I mean, a moment was like a time you had with, like, you know, your significant other. I don't know, but now this is a moment is now it's a force times the distance. You get it. So hopefully this makes a little bit of sense, and we can solve this and go with it. So let's do that. So I'm going to pull up my calculator here, and we can plug this in. Now, typically what I'll do is I'll just understand that I have to add these two items to the other side. So I'm going to add them. They're going to be compositive, but 1.2 times 4 times 1.5 plus 3 times, what is that, 4? Okay, that's all that stuff. I'm going to divide it by, what's left, 3.5. Okay, and I get 5.4857. So dy equals 5.4857 kilonewtons. Okay, hopefully you're able to get that. The next step, right, we got sum of the force in the y direction equals 0. I'm just going to leave the calculator. I'll have to move the calculator for a second. So what do we have? We have by plus dy. Those are both going up. We're just going to subtract off our 1.2 kilonewtons per meter times 4 meters minus 3 kilonewtons equals 0. And we should get by equal to some value here. But I'm going to pull the calculator for that one, because what I'm going to do is I'm going to say 1.2 times 4 plus 3. Why are they plus? Because I added them both the other side. Okay, and then I'm going to do that, and then I'm going to subtract off my 5.4857. Okay, and I'll get 2.3143 kilonewtons. And if I keep going here, I'm going to sum forces in the x direction equals 0. And when I do that, I'm going to say, oops, I didn't even draw it on my free body diagram. Let's get this in here. Let's get a bx in there. And I'm going to say, okay, that's great. I got bx minus 3 kilonewtons equals 0. So bx equals 3 kilonewtons. So these are our three answers. That's 3 numbers. That's 3 things, not 4. Okay, so we got 3 things, and these are our 3 answers there. So hopefully reactions you're golden on, and hopefully this makes a little bit of sense, and you know, and you can get to this level. Now we're not done. What this asked for was the reactions B and D and the load shear moment diagrams. So let's go to the load shear moment diagrams next, and I'm just going to do this. I'm going to draw in some lines here. Oops, let me move that over just a hair. Okay, and what else? Let's do another one here. Just okay, and I'll do another one here and another one here. So I like putting these lines down even if I can't draw super straight. The computer corrects it for me. Isn't that nice? It is a little bit. You should use a ruler because that's even better. But let's think about this here. I'm going to have a shear diagram that looks like this, and I'm going to have a moment diagram. And these are just arbitrary lines that I'm going to draw across here. Okay, so these are my arbitrary lines, and that's okay. But I'm going to call this shear in kilonewtons. I'm going to call this moment in kilonewton meters. Okay, so these are my this is my setup, and what do I need to do first? First, I need to follow my shear, right? So my shear here, I'm going to start at 0, okay, and then I have to pick up this 1.2 kilonewtons times a half a meter. So I need to drop in this distance. What's 1.2 times a half? That's going to be 0.6. So I need to come down 0.6. Okay, so if I come down to 0.6, I'm just going to make each box. Maybe I'll make each box. I'll do this a little bit smaller here, just to make sure I have space. So I come down here, that's going to be down to minus. Right, this is going to be minus 0.6, and again, that comes from that we're dropping 1.2 kilonewtons per meter times 0.5 meters, right? So that got us down to this level. What happens next? Well, what happens next is by is going to take us up, right? So how much is by? By is 2.3143. So if I do this, if I say minus times 1.2. So that's my, no, maybe this makes more sense. Minus 1.2 kilonewtons per meter times a half a meter. Okay. Then I have to add in, well, actually, let me do this. That gets me down to the minus 0.6. Then I have to add in my BY reaction. BY is going to be 2.3143. And if I add that in, I get 1.7143. So basically, BY is going to bring us all the way up to about here. And let me change it back to blue here. That's going to bring us all the way up to here. That's going to be 1.7. Oh, what was that? 143? Okay, that brings us up to 1.7143. Now, R is going to be 3.5 times 1.2. Right, so all I'm going to do here is I'm going to say minus 1.2 times 3.5, and that's a syntax error. That doesn't work. So now I do this. If I get that right, it's going to be minus 2.4875 or 57. Okay, and so that's going to bring us all the way down to about here, minus 2.4857. Let's draw those and connect the dots. Okay, I should probably connect the dots a little bit better there. That's maybe there. Maybe there. Okay, so we got down to 2.4857. Lastly, we're going to come up here, and specifically we're going to come up dy. So if we think of dy is 5.4857. So if I just add in here, I'm going to go back up and find that 5.4857. There it is. There it is. Okay. And I add that in, and I get a value of 3, which is good news because when we look back here, what's going to happen? This is going to come all the way up to 3, right? And then it's going to come straight over, and then this 3 kilonewtons here is going to drop us back down. And what's going to happen is I'm just going to come back down to 0. So that becomes my shear diagram. Now it should be pretty straightforward. So hopefully that makes a little bit of sense. Typically what I like to do is I like to shade these in. So I like my my negative values to be kind of this pinkish or reddish color. Okay, so I'm gonna do those in pink or red. Now I like my positive values to be in this green color. So why not green? There we go. All right, so I like to shade them negative and positive, just make it a little bit clearer. Okay, so these are some of those values here. Now what we also need to do is, what I like to do is I like to drop one more line down here to show that this is kind of going to be the place of where we expect there to be a maximum moment. So where the shear is 0, we expect the slope to be 0. So that's going to be our maximum. Our maximum moment. So let's take a look at this. We have to find some areas. Now the way that I like to label these, and you can label them different ways, but for our areas, what we're going to do here is we're going to say A01, and let me label these lines. Okay, so let me label these lines. It's going to be 0. Let's label this 0, 1, 2, 3, and 4. So I like to label those lines, and then basically I'm going to take the area from 0 to 1. So this area in here is going to be equal to, since it's a triangle, it's minus 1/2 times minus 0.6. Okay, because that's the height, and then the distance we know is 0.5. So the height, this is a kilonewton, and this is a meter. So we're going to get kilonewton meters. So when we look at that, 0.6 times 0.5 times that's a lot of stuff. Let's just look at it. So 0.6 times 0.5 times another 0.5 is going to be minus 0.15. So minus 0.15. Okay, so there we go. So we got that. Let's go to A12, this area here. What are we going to do? We're going to 1/2 times 1.7143 times the distance. Now the distance we don't know here because that 1.7143 in this distance, you'll notice it's not really symmetric. It's actually somewhat close to the middle, but it's not in the middle. To get this distance, we have to think rise and run. We know the rise is 1.7143. The run is going to be this 1.2 kilonewton per meter. So that's the slope. That's how much this is changing. So what we're going to do is all I'm going to do is I'm going to do 1.7143 again, divided by 1.2 kilonewtons per meter, and that's going to give me my distance for that triangle. So if I do that one out, let's bring this up, and I'll say 0.5 times I like to just pull these numbers in here if I can, because I've got them in the calculator. Why not? So a lot of times what I'll do is I'll just square that and then divide it by 1.2. So that's how I put it in the calculator. I mean, you can put it in the calculator however you want, but that's the way I like to do it. So that's going to be 1.22. Let's just go to 4. It's 4 kilonewton meters. Okay, this is kilonewton meters as well. And then let's just keep going. So A13 is going to, or I'm sorry, 23 is going to equal 1/2. Again, another triangle, minus 2.4857. So that's this value down here. That's kilonewtons. You know, these are all kilonewtons here. That's our shear. Times, again, that the distance, it's an absolute value. So we're going to take the positive of the shear, 2.4857, divided by 1.2 kilonewtons per meter to get our distance. Okay, so when we're done with that, let's see what we get. And 0.5 times that 2.4857. I'm going to square that and divide it by 1.2. I'll get minus 2.574. Okay, that's kilonewton meters as well. And then A34, this one's a little bit easier because it's a rectangle. And rectangles are easier, but the rectangle, you can't really see it. So this is a height of 3 kilonewtons. It's a distance of a half a 0.5 meters. So what we'll do here for A34 is I'll do 3 times a half. 3 kilonewtons times a half a meter. That's just going to equal 1.5 kilonewton meters. Okay, and so hopefully that makes a little bit of sense. Now for the moments, we have to go take one more step here, and to get the moments, we're going to start with the moment at 0. So the moment on this line is going to be 0. We're going to start at 0. There's no end moment applied here. There's no, like, you know, when we come up to our free body diagram, there's no end moment here. That does not exist. So we're going to start at 0. The moment at line 1, this moment at this line right here, is just going to be the moment at 0. So 0 plus A01. So when we add A01, we get, you know, minus 0.15 kilonewton meters. So that's a pretty small number. It's just like right in there. So pretty small in there. I'm just going to plot it in. Normally what I suggest you always do is you just label these 0.15, right? And we already have the units over here, kilonewton meters. So that's pretty good. So the M2 is going to equal this previous moment minus 0.15 plus the next area, A12. So this is where I like to just get a running kind of tally in my calculator. I like to just go like, okay, wait. I got minus 0.15 plus 1.22, right? That's the next area. And I'm going to get 1.074. So this is going to be equal to 1.074 kilonewton meters. Okay, so that's that value. And then at M3, the next, that's my 2 line. My 3 line is just going to equal that previous one, 1.074 plus A23. So then we just add the next area, right? This next area here. If I pull that up, I'm just going to say plus. And this isn't, it's a negative, so actually it works out. So it's a negative, so let's put it in here as a negative. And we get 1.50000, a lot of zeros in 1. Now what I'm going to do is I'm just going to run that because, you know, hopefully you do too. So I'm going to get this equals to minus 1.50 kilonewton meters, and then M4, and maybe I'll just move this all up just a hair. M4 is going to equal minus 1.5 plus A34, and what you can see is A34 is plus 1.5, so that's going to go back to 0 kilonewton meters. So we end up at 0 here. I think we're down at minus 1.5 here, and we were up at 1.074 here, 1.074 kilonewton meters. Okay, so this is our moment diagram, and this is a good thing. The height of the shear is equal to the slope of the moment. I like to say that because it helps me to understand how to draw this diagram. So when I think of the height of the shear, I think of, well, what's the value of the shear? The value of the shear is equal to the slope of the moment diagram. So if we start at 0 here, we have a 0 slope. So this is a 0 shear, so we started at 0 slope. Then if we go to a negative value, we're going to have a slightly negative slope, right? So this is a negative slope, and that's going to give us a slight curve here. So this is going to curve down. And then as soon as we get past this point, this line 1, we're going to go to a positive value of shear. So that positive value is going to give me a positive slope, right? So we have a negative slope and positive slope. It looks like a winking pirate. I don't know what it is, but it kind of looks like, I don't know, a winking angry bird. So what's going to happen next? It's going to go up until it hits this point. At this point, we have a value of 0 for that shear. So this is going to go to a 0 slope. At this point, we have a negative value, so we're going to go steep negative again, and then we can connect the dots here. And I don't know, how did I do? I did okay. Not perfect, but we're going to have a curve that connects the dots. And lastly, what you see here is we have a constant height shear, and that constant height shear means we're going to have a constant slope. So a positive constant height shear means a positive constant slope. So we're going to come up with a line here, and this is our moment diagram, which is kind of cool. So again, I like to sort of shade this in, and I don't know if I can do this, but let's try it. How'd I do? Did okay. And then let's come in here. So I like to shade this in. Not bad. Okay, and then we have some negative going on in here. Okay, moment diagram. And this is kind of as complicated as, I shouldn't say it's complicated. It could get more complicated. But if you can do each of these steps, if you can solve for reactions, right? If you can plot the shear diagram and just follow the forces that are, the vertical forces that are acting on that beam perpendicular to the beam. If you can then come and find the areas of those shear diagrams, and then from there, go over here to the moments, and then plot your moment diagram of the slope kind of, things, looking at the shear diagram to help with the slope. That's going to be the key to doing a good shear moment diagram. So this is, a reasonable shear moment diagram, and hopefully you can get there as well. All right. So from here, what we're going to do is we're going to do the next couple sets of problems here, but we're going to go and find a couple stress values. Okay. So let's go and we'll find the maximum normal stress due to the axial load. Now with this, I'm just going to take a time out for a second, because the axial stress, and when we look at this, the centroid composite moment inertia, I'm actually going to skip to C a little bit first here, because when we find the centroid, we have to find the area, right? When we're looking at maximum normal stress, you remember the normal stress formula? If not, let's go to our formula sheet. This formula sheet has a couple different formulas in it. Specifically, when we look at, actually it's up here, but the axial stress formula is going to be this force over area. Okay, so we have to get the total composite area of that system, and honestly, we're going to do that in part C. So let's jump to part C and do that first. So the first thing that we're going to do is we're going to find the centroid, and I still have a highlighter on, but here we go. We're going to find a centroid. Okay, so we're going to find our centroid, and let's go. Let's do it. So to do that, what we're going to do here is we're going to say, okay, well, what I like to do for centroids, and again, if I come back to this, the way that I like to do my centroids and moment inertias is I like to come up with these tables where I have my part, my AY, my AY, and then my my Y bar is some AY over some A. So I like to use this table. For my moment inertia, it's very similar. Part I naught AD 80 squared. But let's first start with the centroid, and then we'll come back. So I'm gonna say what my part. And I just number these, my part 1 and part 2, right? So part 1 is going to be, in this case, it's a rectangle and then a circle, right? So we have two things going on here. We have a shape that kind of looks like this, right? It's a rectangle and a circle. Those two are together. They're not separate here, but I'm going to separate them just so that we can highlight the different parts, right? In this what we have here is something that's 10 millimeters by 40 millimeters, and this has a diameter of I think it's 40 millimeters as well. So we can just go double check that. But yeah, if you see this, what I'm going to do is I'm going to label this kind of like part 1, right? And then if I use a different color down here just for fun, I'm going to use this as part 2. So these are going to be my parts that I'm going to use. Oh, actually, I was wrong. This is 30 millimeters. So let's go and go with 30 millimeters. So I don't know, all my numbers are wrong. Let's see if we get it right. So this is going to be 30 millimeters. At least I found that before I screwed it all up. How's that sound? So 30 millimeters. All right. But when we do our centroid, the next thing that we have to do is we have to find our area. So the area of a rectangle, fairly straightforward, 10 times 40, that's just going to equal, what's that, 400? 400 millimeters squared. Okay, the area of a circle is going to be pi times r squared. In this case, r is 15, so I'm going to square, right, just 30 divided by 2. So let's come back to our calculator here, and actually I'm just going to write this in. So pi, that's going to be 225 pi, right? So pi times 15 squared is going to be 225 pi. And then if I add all this up, I'm going to get my sum of my areas, right? So this is going to be my area. So 400 plus 225 pi. Right, all I'm doing there is 400 plus 225 pi, and I'm going to get 11, let's just go to 1107. So we'll go 1107 millimeters squared. Now I'm going to pause for just a second here because this is what I wanted to do. I wanted to find my maximum neural stress. If you remember, stress equals force over area, right? This is that area. This area is what we're going to use up here. But I'm going to keep going and finish the centroid. But I just wanted to show you that. That's the area that we're going to use. The area of the whole cross section we're going to use. Let's look at y here. So why did we do all this? Because you guys can do awesome things. So actually, I'm going to bring this up here. Why not? Y is the distance from a reference axis to the centroid of the part. So if this is my reference axis down here, I have to come to the centroid of this part. This is going to be the centroid to the circle, and this, up here is going to be the y to the center of the rectangle. So if the center of the circle is probably the easier one, that's just 15, because from this bottom reference axis to the center of the circle is just 15. But if we go all the way up to here, we have to go 30 plus another 5. So that's going to be 35. Okay. And then we're going to go to A times Y. And, I'll bring the calculator up for this. But basically, what do we have? We have 400 times 35. And we have 225 pi times 15. Now, if you think of it, this is almost like a sum of moments equation, which is partly why it gets thrown into statics, which is pretty cool. But, if you're sitting down, maybe that went over your head. I don't know. Let's keep going. So what do I get here? I get 375 pi. Okay, so if I add that, if I add these two together, I'm going to get 24,603. So 24,603, that's millimeters cubed. And then we just have to do our centroid. Our centroid is going to say y bar equals the sum of ay over the sum of a. Right, this one over here is the sum of ay. So now I'm just going to divide these two lines. So 24,603 divided by 1107, and let's see what we get. So I'm going to, in the calculator, I can just take this value and divide it by my, where was my 1107? There it is, 110688, whatever. Okay. I get 22.23. So 22.23. So 22.23, that's millimeters. And I'm just going to pause and provide a sanity check real quick. Does it make any sense? It doesn't make sense that the center of mass of this shape up here is about 22.23 from the bottom. And I think the sanity check says yes, because 15 is just the circle. It's going to be somewhere between 15 and 35. 22 seems actually fairly reasonable based on the areas and just thinking about this thing a little bit. So 22 seems reasonable. So let's take it. Okay. You know what? And let's just finish this out. I'll go back and do the stress in a minute, but let's just finish this out. So let's do moment of inertia, and we'll take this one next, and then we'll jump back up to part B. So moment of inertia. Okay, so the moment of inertia, we're going to do something similar to what we did before. We're going to take this this sheet here, and we're going to take this table where we have to do I naught A D and AD squared. Okay, so these are those same kind of things, and let's jump into it. So we're going to do the same parts, right? We have part 1, we have part 2, and I'm not going to write those out, but I naught is the basic moment of inertia of each of those individual parts. So for a rectangle, do you remember what it is? I for the rectangle is equal to, do you remember? If not, it's in here. I promise it's in here. But look here. The rectangle is bh cubed over 12. So the base times the height cubed over 12. The circle is going to be pi r to the 4th over 4. Okay, so let's look at this. What we have is bh cubed over 12. And I for the circle is going to be pi times the radius to the fourth over 4. So what's this? This is going to be b, which is the base, okay, which is 40 times 10 cubed over 12. The 10 is the height, okay, and the similarly for the circle, we're going to say that pi times the radius, or 15 to the fourth over 4. So these are going to be some values here. We're going to get those out, but I need the calculator to do those, just like you probably need the calculator to do those. If you can do these without the calculator, please teach me how. I know there's a way. I mean, this one's probably a little bit easier than the one with pi. Like, right, we could say, 4 over 12. I'm not even going to go to it, but that's 1/3 of 1,000, kind of thing. So it's actually 10,000. Just getting an extra 10 there. So 33 millimeters to the fourth. Pi times 15 to the fourth divided by 4 is going to be 39. That's kind of big, isn't it? That seems kind of big. Let's go with it. 39,760. So 39,760. Or I'm sorry, 761. Let's do a 1 millimeters to the fourth. While I'm here, I'm going to add those together. So I'm going to take this and I'm going to add the 33, and I'm going to get a sum of I naught equal to 43,094 millimeters to the fourth. Do you see what I did there? So when I'm doing my moment of inertia, eventually I want to say my moment of inertia x equals the sum of I naught plus the sum of AD squared. I like to write it that way. I like to separate those two sums out because of this tabular approach to solving it. I like to sort of separate it out. So we're going to take this one, which is going to be the 43,094, and we're going to add to it some sum of AD squared. Now we haven't done the AD squared part yet, but that's the first part of this complex moment of inertia. Right, to do the next steps, we're going to find A, and the good news is we already found A. We already have 400 and 225 pi. We need to find D. D is the distance from the centroid to the center of the part. So if I look up here, I'm going to erase this 10 real quick, just because what I want to see is if my centroid, it was somewhere up here. This is my y bar, right? That's the y bar distance, right? That's y bar. Okay. What I see is, let me just draw that better. There's my y bar. What I want is the distance from that centroid to the center of the part, or from that centroid to the center of the part. So my D value is going to be up here or down here. Do you see that? This is going to be like my D1, this is going to be my D2, from the centroid to the center of the part. So how do we get that? Well, we have to subtract from the centroid, right? And essentially what we're going to do is we're going to take, our 35, what I like to do here is 35 minus or 22.23 and get some D value, or 22.23 and minus this 15 to get some D value. Okay, then we're gonna take those D values and find AD squared. So I'm gonna pull up the calculator. We're gonna do those out, but hopefully you've been able to do this as well. So 35 minus, I'm gonna go all the way back up and get my 22.23. Okay, and then I'm gonna multiply that times 400. Actually, what I'm going to do is I'll start over. I'll say 400 times this value, and that value needs to be squared because it's an A times D squared term. So what do I get? I get 65,253. Okay, let's go with it. So 65,253, and what was my value here? It's 12.77. Okay. And then the other one, let's do the other one here. Let's do our 22.23 minus 15. It's going to give me 7.23, right? And then what I want to do here is I want to take my 225 pi times that value squared. Okay, so my A times D squared, and I get 36,926. 36,926. So what you can see here is this 65 is so much bigger than the moment of inertia of the flat plate, right? It just that D squared term really adds a lot. But what I can do here is I can add these two together now. So I can take my my 65 and I can add it to my 36, and I'm going to get a total of 102,179. Let's go with it. So this is my sum of 80 squared is equal to 102,179 millimeters to the fourth. How'd I do? Did I do okay? I hope so. So 102,179 here, and if we add all this together, we're going to get Ix equal to, let me just add in that plus our 43. If I come back and find my 43 up here, I'm going to get a total of 145,273. Okay, 145,273 millimeters to the fourth. So a big long question. This is going to, something similar to this is going to be on the final exam. You're going to have to go through and solve for both the centroid and the moment of inertia that's complex. And if you use this table approach, it honestly, it breaks it down piece by piece. And I don't think any of the pieces is super crazy, but putting it all together can sometimes be a challenge. So this is the value that we get. So hopefully I did it right, and we'll go with it. And if not, we'll do another video. I don't know. We'll come back. So then let's come back to part B. Part B and really part D are the two stress formulas that we're going to use. So the first one is just our axial stress. Axial stress just takes the axial force and divides it by the area. So here, our axial force, do you remember what it was? It was equal to 3 kilonewtons. So now we're going to divide by, what was our area? Our area was 1107 millimeters squared, right? So this is great. One of the things that I do know this though is I know that 1 megapascal equals 1 Newton per millimeter squared. So if I want megapascals at the end, what I want to do is I want to multiply this one times 1,000 newtons per kilonewton to get my answer here. So I'm going to do, what's that? It's going to be 3,000. Okay, so 3 times 1,000 divided by 1107. Okay, and am I losing a little precision here? Sure, but what do I get? I get 2.71 megapascals. So not a huge value. Actually, I was wrong, wasn't I? I was wrong. Nobody found me up here. Nobody found me out. Oh, shoot. If you were wondering why I put 3 kilonewtons here, I am too. It's not 3 kilonewtons. See it? You probably saw it earlier. And you're like, yeah, I see it. Because BX, and it's not 3 kilonewtons. It's 40 kilonewtons. So let's just that's right. This should have been 40, and this should have been 40. Okay. So let's go with it. Let's just say BX equals 40 kilonewtons. And if you stopped the video earlier because you were like, this is so annoying, he got it wrong. Well, I figured it out eventually. Let's go with it. Okay. That's the beauty of having notes in here. So let's go with this. We got 40 kilonewtons, and let's redo our numbers here. Okay. So 40 times 1,000 divided by 1107 equals 36.13. So this is going to be 36.13 megapascals. Does that sound a little bit better? I think so. Okay, so I think so. So that's my axial stress. And you'll notice too that if we come back up here, this should be in compression, right? That 40 kilonewtons in BX are pushing these things together. So that's going to be compression. So I'm going to label this. I'm going to call this compression, and hopefully that makes a little bit of sense, right? Because anytime we have something where we have two forces that are pushing on this, trying to condense it, that's compressing, right? That's compression. So let's keep going here and go to the next part of this. The next part of this, I actually give you two versions of this. I'm looking at this and I'm thinking like, okay, with these two versions, what I'm going to do is I'm going to solve for the bending stress at the top and bottom at point C, which corresponds to the point of maximum moment B and D. And then there's another version where we're going to go to D. And the reason that I did this is just to give you kind of sense of bending stress, tension, and compression. Now this becomes really important because the bending stress formula by itself is FB equals MC over I. Okay, this is the formula itself. Now at this point C corresponding with the maximum moment, we know that the moment, we got this from our moment diagram, the point C, and you might be wondering, why did I jump from B to C without a dimension in here back to D? The idea with this is C is going to be defined as this point here. This is going to be my point C, where we have that maximum moment. So that maximum moment is going to be 1.074 kilonewton meters. Right, but this is that moment, and then when we look at this at point D, right, our point D is going to be -1.5. Now these positive and negative moments mean something, right? The positive moment means that our bending is kind of happy. It's a happy moment. If we think about a deflected shape here, right, this deflected shape is going to look something like this. Okay. I didn't want it to go back to a line, but what you see here is this moment right here is going to be kind of positive, kind of happy. Whereas when you go over the support, right, when we go over the support, the moment's going to be kind of negative or sad. The curvature of that deflected shape, right? This is the deflected shape, right? This is this isn't like, you know, this is just kind of like can you picture what this load is going to do to that beam? It's going to deflect it downward, but the support is going to stay up. Okay, so that curvature is one way to think about it. Another way to think about it is positive and negative moment. And positive moment puts compression on the top and tension on the bottom. So when we come down to here, we know our moment at point C equals 1.074 kilonewton meters. Okay, we know I is equal to, we just found I, right? What was I? I was 145,273. So 145,273 millimeters to the fourth. This is great because we actually have just about all that we need. The only thing that we need left in here is C. Now C can be a little tricky, but basically when we think about C, what I want to do here is I have, you know, this shape that looks something like this. And when we think of C, what we're going to do is we're going to go from the centroid of this thing to the extreme fiber and tension or compression. Now, if we think about this, the extreme fibers are going to be at the top or the bottom. So C for the bottom is just going to be, this is going to equal to Y bar. Or that's just the Y, that's the distance from the bottom to the centroid. Now C for the top, though, C for the top is going to be a little bit different. This is going to equal the total height minus Y bar, right? So in this case, our total height here is 30 plus 10, 30, right? Because we have a 30 millimeter diameter plus 10. So this is 40 millimeters height, and that's going to give us our top, which actually, if we know this is 22 point, I think we said 23, right? How's that? Is that what we had? 22.23, right? This top is going to equal, if we do this out, 40 minus 22.23, or that's going to be 17.77, and these are in both going to be in millimeters. Okay, but that gives us these C values. Once we have that, we can come in here and we can say, well, we have the top and we have the bottom, right? And specifically, you can say, well, the FB for the top is going to equal our 1.074 kilonewton meters times C top, which is 17.77 millimeters, divided by the moment of inertia, 145,273 millimeters to the fourth. But again, 1 megapascal, 1 Newton per millimeter squared. So this is where we have some unit conversions in here, because we have kilonewtons and we have meters now. So now we have to multiply by 1,000 newtons per kilonewton, and we need to multiply by 1,000 millimeters per meter. So a lot of unit conversions going in there. But once we do that, we get FB for the top is equal to all this stuff. So let's just plug that into the calculator here. So 1.074 times 1,000 times 1,000 times 17.77 divided by 145,273, and I got 131.4. Okay, so 131.4, that's going to be megapascals. Okay, value. Okay, so that's 131.4 megapascals. And similarly for the bottom, FB bottom, what do we have? This equals to 1.074 kilonewton meters times our bottom value here, so our 23.23. That's millimeters, right? Divided by 145.273 millimeters to the fourth. I need to multiply this by all of this junk again, right? So I just need to bring that back down. And what do I get? I get my FB for the bottom equal to, let me just come back to the calculator here, because all I have to do is I have to come back to this line here, and you'll notice the only difference is going to be this value here, my C value. So if I take 22.23, put that in, that's the only thing that I need to change, and I get a 164.3 megapascals. Now, one of the things that I have to figure out is tension and compression, because this makes a difference. But what we said was positive bending is happy bending. So what that does is it puts tension on the bottom and compression on the top. And hopefully you can see that the top is trying to get smaller, the bottom's trying to grow. And that's so what we can say here is the top is going to be compression, and the bottom is going to be tension. That corresponds to a positive moment. And those are our two answers for bending stress. Okay, so this is good. And we have these two answers. And the last thing that we have to do here, and honestly, like, this will probably be a separate question on the test, where I just give you a moment. And I say, I give you a centroid, I give you a moment, inertia even. And I say, go find the combined stresses, okay? And you have to find the axial stress, you have to find the bending stress, you have to find these combined stresses. But the idea here, again, is we're going to have like a top and a bottom. Okay, but the axial stress, what the axial stress is, or I'm sorry, the combined stress is, we're saying, you're going to say F equals the combined stress equals sigma plus or minus sigma plus or minus FB. Now, specifically when we get into this type of equation, what we're going to do is we're going to say positive is tension and negative is compression. And if we use that sign convention here, that's going to allow us to solve these, because basically all we're going to do is we're going to say, well, F for the top, the combined stress F, is going to equal the axial stress of our, if we come back to our axial stress was 36.13, or let's just do 36.1, but because it's in compression, we're going to put that negative sign in, right? This is compression, right? So that becomes negative. Now, if we think about bending stress as well, what we're going to do here is we're going to say that's also going to be negative, because we know that we have 131.4. Okay, so 131.4 megapascals. That's also in compression. So that bending stress on the top, it's trying to get smaller when you bend it. So that's going to be compression. So if we put these two together, we're going to get some value here, and specifically, what we get for that value is in the calculator. So minus 36.1 minus 131.4 is going to give me minus 167.5. And there we have it. That's minus 167.5 megapascals. Okay. So hopefully that makes a little bit of sense, and we're still cooking, right? And then for the bottom, right, F bottom, what do? We still have minus 36.1. The compressive, that compressive force is equal. It averages out equal to all across the entire face of this thing. So it's equally compressing this thing all throughout. So we're gonna have that minus 36.1 everywhere in axial. So in the axial forces, or I'm sorry, the axial stresses are gonna stay the same on the top and bottom, but the bending stresses are gonna change, because when we start bending that beam, the bottom's going to act differently than the top, because the C value is going to be different. So what do we have to do here? We're going to come back, and we're actually going to add in it with 164.3, because the top is in tension, or I'm sorry, the bottom is in tension. Okay, so the bottom is trying to pull out when you bend this thing with positive bending. That's going to be tension. And when we do all this out, what do we get? So I have to do the numbers out here, but I'm going to get minus 36.1 plus 164.3, and I get 128.2 megapascals. Okay, and this is interesting because even though the bending stress is higher in tension on the bottom, we actually get a lower total overall stress than the top because the tension is reduced by that compression a little bit, whereas on the top the compression and bending is increased by the axial compression as well. So this whole process is what you're going to need to do for like, you know, finding axial stress, finding bending stress, finding a combined stress as well. Okay, so those pieces are something that you need to know how to do. Now I did another one of these just to, again, kind of to really highlight this idea with bending stress, but the thing is, I can take 90% of this and reuse it. So I'm actually going to copy this just to save a little bit of time here, and I'm going to paste this down because support D, it's basically the same. Okay, so it's basically the same, but what happened is that what does change here is this moment went from 1.074 to now it's 1.5 kilonewton meters, right? So this changed, right? The I is the same, the C top, C bottom, that's all the same. So I need to change these values in here. I need to change these values in here. These values are all going to change as well. Okay, so I'm just going to erase a couple things here. But what you see is basically everything's the same except for this moment. Now this moment, mind you, is going to also change because this moment is going to be negative. Now when we think about that, let's just come back up to our deflected shape up here again for a second. If we think about our deflected shape, at this point, we're going at point D, we're going over top of a support. And hopefully you can picture the top is going to be in tension, the bottom's in compression because it's trying to bend over top of the support. The top is trying to get bigger, the bottom's trying to get smaller. That's a negative moment. And that's how we define positive and negative moment. And that positive and negative really is important because it defines kind of where the tension and compression are, right? So if we think of a negative moment here, it creates sad curvature, but specifically what we care about is the bottom's going to be compression and the top is going to be tension. Okay, so when tension's on the top, it's a sad thing. I don't know how you want to remember it, but that means they're going to also be reversed. So the tension's on the top now and the compression is on the bottom. Okay, so really what we have here is 1.5 because those are our moments, and then everything else is just going to be plug and chug, right? And then when we come down here, I'm going to erase these as well because these values are going to change here. Okay, so a lot of the setup is the same, but when we come down to it, the numbers are going to change, and specifically the tension and compression is going to change, whether it's a positive moment or negative moment. So look at your moment diagram. It's a positive moment, that means tension's on the bottom. The negative moment, that means tension's on the top. And that you can use that to really, you know, define these stresses. So hopefully you can do that, and that makes a little bit of sense. But let's just run through the numbers here. So 1.5 times 17.77 times 1,000 squared divided by 145,273. Okay, I'm going to get 183. 183 point, what do we have, 5? Okay, and then if we do the same thing here, and instead I change it to 22.23, I'm going to get 229.5. Okay, and then I'm going to bring those values down here. I'm going to say 185, or I'm sorry, 183.5. And I'm going to say 229.5. Right, and these values are good values, right? They're good values. Let me turn the calculator off for a second. Right, so we have the 183.5, the 229.5. I'm going to bring those values down here. So the top is going to be the 183, the bottom, you know, bending stress is going to be 229. Right, that's just saying the axial stress is the same across the entire section, but the bending stress changes whether it's on the top or the bottom of the member. Okay, and then what I need to know is, because this is negative moment, the top is going to be tension and the bottom is going to be compression, which is going to impact these signs. So this positive is tension, negative is compression, and this is where we get some of we get our values now. So what do we have? It's minus 36.1 plus 183.3.5 and minus 36.1 minus 229.5. So I get values of 147.4 and 265. 0.6. Now it should be said here that this positive value stays tension, the bottom the negative value stays compression. So I don't think I did that on the previous version, so I'm going to go back and do that again. But again, yeah, the whole idea here is trying to figure out how does the combined impact of axial compression and bending, whether it's positive bending or negative bending, how do those two interact together? Right, so in this case up here, the negative sign corresponds to compression, so the top would be compression. The positive sign corresponds with tension, so the bottom would be tension. So whether we're looking at this is I think this was point C, or we're looking at point D down here. Right, these are the values in what I kind of wanted to go through one positive, one negative, just again to really hit home on that tension and compression thing, because that's going to be important in understanding how to combine stress. It's also going to be important in understanding how they impact each other, whether they add together or one offsets the other. So these types of problems are important. Now we're pretty far in already. We're an hour into this video. Okay, we got a lot going here. This is a lot of this is a lot of work, okay? And I get that, and I'm sort of stopping, I'm pausing, I'm doing multiple versions of this, but you got to master this stuff, right? If this is a 2-hour test, you got to master this stuff. You can't be fumbling around or thinking back, or trying different problems and things. You got to master this. Same way, I want you to master some truss problems. So here, I'm not going to make you solve for the truss reactions. Sometimes I need to. I don't always need to. Like this, actually, I love this joint here. So this joint is kind of neat because I don't even have to solve for the reactions. I will need to solve for the reactions eventually. So let's just solve for them and we'll go with it. So what do I have here? I've got some truss that looks like this. Okay, and it's gonna look like this. So I got this truss, and let's solve reactions. This is just good practice. It's why not? It's good practice, and let's just do it. Okay. Okay, so I've got this truss here, and I need to solve reactions. Can you do it? Can you pause the video and solve reactions? Okay, I think so. What do we have? We have Fy, we have Fx, and we're gonna have Hy. Okay, I got 14 kips down. I've got 3 kips to the left, and I've got 8 kips down here. So hopefully this is second nature to you at this point in the course, but some of the moments about point, I'm going to do F now equals 0. Okay, so what do we get? Some of the moments about point F, I'm going to say Hy times 2 panels at 6 feet. That's going to be times 12 feet, right? This distance here is 12 feet. Right, and then this distance back to this one is going to be 6 feet. So this is interesting. I'm going to add 8 kips times 6 feet. Why did I add it? Because if we think about this force, it's coming down this way. That matches our positive sign convention. Okay, maybe you can't see that. Let me try a different color here, but this force is causing rotation this way, which matches our positive sign convention. Okay. That's going to be 8 times 6. What else do we have? We have the 14 and the 3. I'm going to just write it on the new line here, but minus 14 kips times a big long distance here. This distance to the 14 kips, that's 3 panels, so that should be 18 feet. Okay. So what's that? It's times 18 feet. And then I'm gonna add in the 3 kips times 4 feet. That all equals 0. Why am I adding in the 3 kips again? If we think about this, it's going in a counterclockwise direction, just like our positive sign convention. Okay. So if you can write that equation out, you're getting there. So let's just let's go in. Let's solve this equation. And what are we gonna get? We're gonna get I'm going to add the 14 times 18 to the other side because this is a negative. So I'm going to first start by adding that to the other side. Then I'm going to subtract off 3 times 4, and I'm going to subtract off 8 times 6. So this puts it all on the other side. I didn't write that out, but that's 192 divided by 12. That's going to be 16 16 kips. Okay, so hopefully you got that value as well. The last two equations, what are we going to do? Sum of the force in the y direction equals 0. Fy plus hy minus 8 kips minus 14 kips equals 0. So what do we get? We get Fy equal to, what's that? 8 plus 14 minus 16 is going to be 6 kips. Okay. And lastly, let's see if I can do this one right. What are we going to do? We're going to say sum of the force of the x direction equals 0. So if we're doing that here, we're going to say fx is to the right minus 3 kips. There's that 3. To the left, so fx equals 3 kips. Okay, we got some answers here. I believe they're right. If not, just let me know. But I think we're doing all right here. We're going to take those values, and then we're going to go ahead here and finish solving our truss, right? So this is one of those truss problems that I think I think if it's going to show up on my final exam, I'm just going to let you know. It's not going to look necessarily exactly like this, but it's going to show up in some way, shape, or form, whether it's rotated 90 degrees or 180 degrees or flipped or mirrored or something. It's going to show up. But what I want to do is I want to solve for forces A, B, and AF. Now, honestly, on the final, I'd probably just leave the reactions off. Why am I saying that? Because I can give you a cantilever truss, a truss even like this one. To solve for AB and AF, guess what? We didn't actually have to solve for reactions. This is just good practice. Okay. You might say, well, why not? Let's look at this. If we come back here and draw a free body diagram, joint A. Okay, joint A, what does it have? It has a joint. It has got a little bit of a member. It's got a little bit of a member here. Right, this is joint A. And also we know that we have 8 kips acting down. Well, in order to cut that joint free, right, in order to cut that joint free, we have to cut through this member and this member here. We have to cut through AB, and we have to cut through AF. They're going to leave forces, right? So we have to draw those forces in. So now I'm going to have this force here. I'm going to call it AB. I'm going to have this force here, and I'm going to call it AF. Do you remember how to do this stuff? If you want a quick tutorial, there's a little bit of a thing in here on our formula sheet, right? So I put some of this with the method of sections, method of joints. Some of this stuff is in there, and granted, it's flipped around. It doesn't look exactly the same, but it should give you all these steps, right? So we isolate the joint, we solve for the force in the x and the y, we do some trig, we do some some force in the other direction. So let's do that here. And specifically, what I like to do is I like to show these components out. I like to show AFX and AFY. And when we do that, actually, I'm just going to move this over just so we have a little bit more room here. Right, when we do this, one of the things that does for us is it shows in the vertical direction we only have one unknown. We have AFY. In the horizontal direction, we have 2 unknowns. We have AB and AFX. So what that tells me and what that informs me is I'm going to start by summing forces in the vertical direction. Sum of the force in the y direction equals 0. And when I do that, what I see here is minus 8 kips minus AFY equals 0. Now I've been doing some fancy math, but this hopefully isn't too crazy. If I take the AFY and add it to the other side, minus 8 kips equals AFY. What I see is AFY is a negative 8 kips. That negative sign means my initial arrow is drawn in the wrong direction. So it's in compression. I drew it in tension, I assumed it in tension, but that negative sign says this arrow is in the wrong direction, so it's actually in compression. Okay, so that's the first step, is just to solve for that. The second step, what I like to do is I like to call them the force geometry triangle kind of thingy. That's the technical term. But what I like to do is I like to say, okay, if we have member, if we go from A to F here, okay, so A to F, right? This is A. This is A and this is F. I know that this distance and this distance is going to be, I think this was 6 feet and 4 feet. So I know these two distances. Okay, if I know those two distances and I want this force to line up with that member, it's a two force member. Remember, these forces have to line up with that member. For that to be true, that means my force, AF, has to be similar to this geometry triangle. Okay, so I'm going to have AFX, and I'm going to have that's AFY and AFX. Okay, so these two forces have to, or these two triangles have to be similar. So here's my force triangle, and here's my geometry triangle. right? So those two have to, and they're going to be similar. So if they're similar, that allows us to solve something here. So what that does is now I can say, okay, well, if they're similar, what I can do is I can say, well, AFX divided by AFY equals, the x over the y means 6 over 4, 6 over 4. So when I solve this out, what I'm going to get is I'm going to get AFX equals 6 over 4 times AFY. And if we think about that here for a second, we had AFY was, what was AFY? AFY was minus 8. So minus 8 times 6 over 4. It's just going to be minus 12. You see it? So minus 12 kilonewtons. Okay. And that's a good thing. That gives us our value here. But it also, if you remember Pythagorean's theorem, since we have this force triangle, we can use Pythagorean's theorem and we can say, well, AF, it has to equal the square root of AFX squared plus AFY squared. So we do that math out, and I'm not going to do the substitution here just for the sake of time, but what do we have? We have essentially the square root of minus 12 squared plus minus 8 squared, and we're going to get about 4 root 13, which I don't really like the radicals. I'm going to get 14.42. 14.42 kips. And if we think about this, this is going to be like a plus or minus. I'm going to keep that negative sign just to remind myself that this is going to be compression also. Because if those internal values are negative, this external value is also going to be negative with the way that the square root works. Now, you can't take square roots of negative numbers, right? But these squares are going to get rid of the negative. So the 14.42 hopefully makes a little bit of sense. But that gives me the one value. And then if we come back here and we just sum forces in the x direction equals 0, what we can see is AB plus AFX equals 0. And you might be thinking, like, isn't AFX minus? Yes, it is, but the arrow's going to the right and AB is going to the right. So I'm going to put both of these as plus. I'm going to AB plus AFX here, which is minus 12 kips, equals 0. So when I substitute this in, so I draw the arrow in the right direction. So when I do my equation of equilibrium, I have my plus AFX, and then I'm going to have this minus 12 here. So AB, when I add it to the other side, it's going to become positive again, meaning my arrow is drawn correctly in the right direction. That means AB is going to be tension. Okay, so there's a joint for you, and that is, the type of thing that very, 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 very well is going to show up on the test. And granted, it might not look exactly like this joint, but it's going to look very similar. I'm not going to make you suffer so much probably to give you two members at angles. I'll probably have one at an angle and one not at an angle. Okay, can you do this? Can you solve for either of those members or both those members in a reasonable amount of time? Okay. I hope you can. The next part that I'd probably give you is something where you have to do method of sections. Now, method of sections, if we come back up here, actually, let's go to the problem statement real quick. But CD and GD are the two next forces that I want here. So if we think about this, CD and DG, we could do method of joints and just brute force our way across and brute force our way across down here. I'm not going to. I'm going to use method of sections. Specifically, I'm going to take the right-hand section. This is where we needed to know HY. Now, I could have just given you a force down here. I could have said instead of HY, I could have given you a force down here. I could have given you a force of 16 kilonewtons. All right, so if I gave you like a force here of, 16 kips, I could just say, okay, if that's true, you could take a section like this is our section, right? And then you could solve for CD and DG. You could also solve for HG using this section, but the question doesn't ask for it, so we're only going to do the two members, right? So let's draw that section on the next page and go solve it. So our section is going to look like this. I'm going to come down 4. I'm going to actually, let me do it right here. I'm going to do down 4, back up and back over. So this is my section. Specifically, I could lay out I could label some joints. So this is going to be D, this is going to be E, this is going to be H, right? These are my joints. I know that I have a few forces here. So HY, which was HY was 16 kips. Okay. I also have this force down here based on the original diagram, 14 kips down. And I also have this force here, 3 kips. to the left. Okay, so a bunch of forces, and you know, looking good. Then I'm gonna have some forces here. So I'm gonna have CD. I'm gonna have, you know, GD, or no, I call it GD here. So let's call it GD here. And then I could also have what's this called? This is gonna be called HG, because we have a point over here that's called G, and a point over here that's called C. So those points are not actually in the diagram. I'm just drawing them because those are points, they're reference points that are going to be useful. Now, because I put CD first, what I like, well, let's just try to see if we can solve CD first. So one of the things that I look for with method of sections is I look for ways to sum moments. And if we look back at the formula sheet here, one of the things that I put in this formula sheet, and granted some people like this and some people don't, but what I like to do is I like to sum moments at the point of intersection of two unknown member forces. That's going to help me quite a bit. So if I think about this for a second, I've got a member force. I've got a member force here that's called GD. Okay, I've got a member force here that's called HG. And what you see is right at the intersection there, I have an intersection of two forces. Now that's a great place to sum moments, because if we don't know those two forces and they pass right through this point, if we sum moments at this point, they're going to cancel out. They're not going to be in the moment equation, because the moment's a force times the distance, and the distance between that the line of action of that force and the point is 0. Okay, so I'm just going to erase that for a second. But what I'm going to do here is I'm going to say, okay, I got this. So if I sum moments about point G equal to 0, what I can do is I can solve for CD. Okay. So let's try it. If I sum moments about this point here, right, this point G. Okay, it's not on the diagram. That's okay. We can sum moments about any point, and this thing still needs to be in equilibrium. What I'm going to get here, though, is CD times 4 feet, because my distance to between C and G is 4 feet. Okay. I'm going to have this HY times 6 feet. Okay, so let's add that in. So I'm going to say plus HY times 6 feet. Okay, what else do I have? I have this 3 kips and 14 kips. So if I think about this, I've got 14 kips times 12 feet. I'm going to subtract that off, minus 14 kips times 12 feet. And then I'm going to add in 3 kips times 4 feet, because this 3 kips, again, is 4 feet vertically away from that point G. This all has to equal 0. And if we think about directions again, let's just think about directions for a second. CD is coming this way, HY is coming this way, 3 kips. They're all going counter clockwise, so those are all going to be positive values. So you get positive CD times 4, positive HY times 6, positive 3 times 4 in here as well. So if I take that away here, what we can see here is also this 14 is going the other direction. That's why that one is negative. But the good news is, once we get this free body diagram, once we get this drawn in, I know that HY is equal to 16 kips, right? So then what I can do is I can just come over here and I can do the math, right? So I can say, okay, 14 times 12. I'm going to add that to the other side, so I'm going to flip the side, and then I'm going to subtract off minus 3 times 4 and minus 16 times 6. Okay, I do that. I divide it by 4, and I'm going to get a CD equal to 15 kips, and that's going to be a positive value. I'm going to get CD equal to 15 kips. Positive values. The positive value means my arrow is drawn in the correct direction, and specifically that's going to be tension. Okay. Force number 1. One equation, one force. Wouldn't it be nice if all of life was like, I don't know, actually you're like, no, I don't want life like this. That's too complicated. There's a lot of numbers in there. But well, let's go with it. Okay. The next part of this, and honestly, I sort of skipped this when I came into here, but when we look at this method of section for parallel cord trusses, the first thing we need to do is sum forces X or Y. I sort of skipped down to step 5 here, but steps 3 and 4 are perfectly valid, and we're going to do that here, because what this does is it allows us to solve for one component. So like in this sample here, the only vertical component that we don't know is ADY, so we can solve for that directly. So let's come back here. and do that. And specifically, when we think about this, we're going to have this dgy and dgx, right? So when we sum forces, what I see is I see one force in the y direction that I don't know. So I can take some force in the y direction, and I can say, okay, well, I've got minus dgy because it's going down, minus 14 kips because that's going down, plus 16 kips, which is hy going up. S equals 0, right? So I'm just adding all the forces in the y direction. So dgy, hy, and 14. And what I get here is if I add dgy to the other side, is minus 14 kips plus 16 kips equals dgy, and dgy equals 2 kips. Okay? So there we have it. We get a positive value again. That positive value means tension. Okay? We have part of our answer, and we're not done, because once we get one component of a truss member, we can use this to solve for the remainder of that truss member, right? We can use our force in geometry triangles, and specifically here we have a triangle that looks like this. That's 6 feet, 4 feet, and some feet. I don't know what those feet are, but let's go with this. This is G and this is D. And then also what we're going to have here is this force GD, and we're going to have, coming down GDY and GDX. Okay, so we have our values here, and all we have to do is, since we know the y value and we want the x value, I like to do the unknown on top divided by the known equals, so if we have x over y, we're going to do x over y, 6 over 4. Okay, so GDX equals 6 over 4 times GDY, or that's, 6 over 4 is 1.5. 1.5 times 2, that's just going to equal 3 kips. And then we can say GD equals the square root of GDX squared plus GDY squared, which is going to be the square root of, what's this, 3 squared plus 1.5 squared. Not 1.5, I'm sorry, 2 squared, which is going to equal, I don't know, I can't do that one in my head. Let's come up with a number here. Second square root of, what's this? This is 3 squared plus 2 squared is the square root of 13. 3.61 kips. And again, because this is in tension, this is in tension, and this is in tension. So if you get dgy, the x and the total force, or GD, the total force is going to be tension as well. So this is our answer here for GD, and we're good. I mean, this is again method of sections, kind of base level method of sections that I expect you to be able to do on this test. Could we solve for HG as well? Sure, we could. Honestly, to do that, what I would do is I'd sum moments about point D. Okay, maybe try that. That's probably good practice for you. If we keep coming down here, the last thing that I put on this was determine the axial deformation in member AB. Axial deformation goes back to stress strain elongation, and specifically the formula delta equals PL over AE. I don't know if you remember that one, but it is on the formula sheet. If you come back down here in the formula sheet, and we look down at this point, the axial deformation is delta is PL over AE. So you just have to be, concerned with the units. I had a colleague, Doug, you're awesome, man. I miss teaching with you. He retired, but he always said the hardest part is the strength of materials is statics. And the reason he would say that is because to find this P force, we had to go through all this stuff, right? So to find the force in member AB, we had to go through all these equations here. Okay, so we went through all this stuff here, and we got this 12 kips. But now we know that this force is we're going to take 12 kips because that's the force, and P equals 12 kips. That's our member force in AB. It's 6 feet long, so times 6 feet. I need to do some conversions here. Typically, I'm going to find these in inches, so inches per foot. Okay, and then I'm going to divide it by the area. The area of these bars, I think we said that in the problem they're 2 inch square, and it's a modulus elasticity of 29,000. So when you get to questions like this, don't miss them. Don't miss them, because 2 inches times 2 inches, right, times 29,000. PSI. Don't miss these questions because these questions are the plug and chug questions. Honestly, the hardest part of this question is knowing which equation to use and finding P, right? P was that value that you had to find from the truss. So once you get that, you can do this, but it takes a little bit of remembering how to do trusses, and just this little bit with the unit conversion, that extra 12. And that's what you need to remember to do. So if I put this all in, I get 0.00745. I mean, not a big number by any means. 0.00745 inches, and that's a small number. It's 100. It's a very small number. Okay, I lost a zero even. 0 0 0. It's 3 0 0 0 0. Okay, so that's a small. No, so it's only 2 zeros. I was wrong. Okay, so 0.00745 inches. So a small number, but that's going to equal my delta for AB, the change in axial length of AB. Okay, and honestly, do you need to be able to plug and chug? Yes. Or do you need to find those forces? Absolutely. And that's why I tell my students, finding these forces is a super, it's not an easy thing to do, but once you get it, it becomes super powerful. It's kind of like your superpowers, is like, if you can do these things, then you can start doing these, the equations to find out axial deformation, to find out stress, to find out if your members are going to actually work. Okay. Last question here, and this question, it was not on any of the homeworks and not on any of the videos, but I started writing some of these questions for my FE exam prep kind of stuff. So this is one of those things where earlier in the semester we took a look at, and earlier in this playlist we took a look at a tensile coupon. I don't know if you remember that, but it was this thing where we had this thing, it's just a coupon where you pull up and down on it with a big load press, and you get this curve, right? This curve is a typical force elongation. So as you pull on this thing with some force, right? So as you pull on this thing with some force, this distance, right? This distance gets bigger. So this is my original length of, I think it was 100 millimeters, right? This is 100 millimeters. But as you pull on it, you can picture this thing getting bigger until eventually it breaks. Okay, the diameter of this thing was 10 millimeters, right? 10 millimeters diameter. That was that's one standard test coupon that's get used. Sometimes there's flat bars too, but this is a standard test that's done to test material strength. And with this, I just gave you some points. So I labeled the points on these diagrams: point A, point B, C and D. And these points relate to various important features of that diagram. Now this diagram is for a typical steel. It's different materials are going to have different diagrams, but this shows various phases, right? And this is where this point right here is known as the yield point. It's where you lose this linear elastic response, right? This linear elastic response is kind of like your spring constant. If you load it up to this point, your spring will go back to where it started, and after that point, your spring will start to permanently deform, right? So this is right up to that point, your spring will go right back. But once you get past yield, that spring is going to permanently deform and stay out. Okay. This yield point. This is the start of strain hardening, right? So at some point, your material actually starts to get harder. It takes more force to keep getting deformation. This range in here is called the plastic range, right? So this is our strain hardening range in here. This is our rupture point. I'm sorry, that's not rupture. What am I thinking? This is our rupture point over here. This is our ultimate point, right? The highest point is going to be ultimate, right? That's our ultimate point, right? That's the biggest force that you can get on this member. Okay, but these values and these kind of this curve becomes important, especially when you start to look at, like, when I teach a concrete design course, we go over stress strain elongation all the time, and it just you have to kind of understand those pieces, because once you get past this yield point, you have a certain stress. Before that yield point, you have a different stress, right? And this is where, you know, if we can figure out this slope here, that slope is going to be our modulus of elasticity, E. So these types of things are super important, and hopefully as you come out of a strength of materials course, you have some sort of an understanding of these. So did we circle the yield point? Yes, we did. That's point A. Okay, so hopefully this makes a little bit of sense, and you have some grasp of this. But the next page, I just wanted to run through some real basic, can I say basic, questions that kind of get to the heart of stress strain and elongation here, or modulus elasticity, really. But the stress in the bar due to the applied force in megapascals, this is at the yield point. So right at the yield point, what do we know? Well, we know that we have 0.25 elongation and 38.69 kilonewtons. So if I want the stress, this is going to be the axial stress. So stress, do you remember the formula for stress? Stress equals what? Force over area. So the force was, what was my force? It was 38.69 kilonewtons divided by my area. The area is going to be the area of this original bar. So what is this? Going to be pi times 5 millimeters squared, and that's going to be my stress. So what do I have? I have 38.69. Actually, let me do one other thing. Let me do a unit conversion here, times 1,000 newtons per kilonewton, and times 1,000 divided by, I'm going to put this in parentheses, but pi times 5 squared. You get 492.6 megapascals. I'm just going to round that to 493 megapascals. Okay, so the yield point occurs at 493 megapascals. Similarly, the strain, let's look at strain. Strain equals the change in length over the original length. So our change in length was, let's look, it's 0.25 millimeters. So 0.25 millimeters divided by original 100 millimeters. What's that? 0.25 divided by 100. We move the decimal place 2 places, so 0.0025. You'll notice this doesn't have units. This is like millimeters per millimeter, right? This is just unitless. A lot of times I'll just leave those units off for strain because it's just a ratio of the original length to the change in, or the change in length to the original length. And then lastly here, the modulus of elasticity. If we remember this formula here, stress equals epsilon E. I think let's look here. What do we have? This, yeah, stress equals epsilon E. So if we want to solve for E, we need to divide both sides by the strain. Okay, so what's this? This means E equals stress over strain, and specifically we got 493 megapascals divided by 0.0025, which is going to be our modulus of elasticity. So let's find that. And does anybody remember the modulus of elasticity for steel? 29,000 KSI, that came up on the previous problem, but in megapascals, it's typically around, remember? Let's go for it. Let's find it here. So 492 divided by this 0.0025, it's typically around 200. So this, if you're doing this you're doing this with an actual lab or something like that, where you're doing this and you get 197 instead of 200, you're pretty darn close. I mean, that's pretty good, actually. 2 significant digits, 197 rounds to 200,000. So not bad. And we ended on a relatively short problem here, but there's a lot that's going on in this test, right? I spent a lot of time with beam reactions. I spent a lot of time with moment diagram. I spent a lot of time on centroid, moment of inertia. I spent a lot of time on stress. So those components are definitely going to be there. There's going to be truss problems, okay? There could be something. There's going to be some sort of axial deformation problem, right? These problems will be on there. And I'm not, it's not going to look exactly like this problem, okay? It's not going to look exactly like this problem. But you have to understand how to do each of these concepts in order to be successful with this test. So Hey, I mean, if you have questions on any of the specifics, definitely reach out, definitely talk to me. I'd love to get there. But at the end of the day, there's a lot of information out there that you've learned in this class, and I want you to do your best to really nail it, to crush this exam, and to show me that you know this stuff, that you're ready to move on to the next class. Because I truly believe that you put in a ton of hard work and that you're there. And honestly, I think these skills are so fundamental that they really, 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 really help when you get into component design, when you get into steel and concrete design, when you get into the next classes that are going to build on these concepts. The better you understand these pieces, I think the better you're going to do moving forward. So definitely feel free to continue studying, continue going through this playlist. But I hope that this is a good kind of wrap up with all this information. It kind of reemphasizes some of the things that you need to know, and it goes over and just gives you some just that quick refresher. But if you have questions, definitely feel free to reach out. I'd love to hear from you. If this class has helped you, I'd love to hear how it's helped. If there are things that you want improved, you can reach out with that as well, and you can fix all my mistakes, because you know what, I do make mistakes, and that's okay, in the sense that we're all going to make mistakes here. The problem isn't making mistakes. The problem is not finding those mistakes. And hopefully you can find those mistakes. You can learn from those mistakes. You can have people check your work so that you don't continue to make mistakes, right? But hopefully, as you learn, you'll continue to grow and grow and grow as an engineer, to do really, really well. So that's my hope for you, is that you continue to just press in, to press on, and keep working hard and moving onward and upward.